Hello, my dear students. Today I am teaching you very important concept about atomic sizes. And today we are going to understand the whole chemistry of the size of the atom because it plays a very important vital role to understand about chemical bondings and to study about their properties. So let us begin with the definition. The atomic radius of a chemical element is a measure of the size of its atom, which is usually the mean or average or the typical distance from the center of the nucleus to the boundary of the surrounding shells of electrons. Means, roughly, if I say the size of the atom, the circle radius means how far its boundary is from its center. Similarly, if we assume that atom is a sphere, so its radius will be the distance from its center to its outermost boundary. Now, there is a problem that we cannot determine the exact and precise size or radius of the atom because of two possible reasons. Reason number one, there is no sharp boundary of an atom because the probability of finding an electron never becomes exactly zero even at the larger distances from the nucleus. Means we cannot say exactly where electron is found or what is its exact boundary. The next possible reason, the electronic probability distribution is also affected or disturbed or changed by neighboring atoms. So, to talk about particularly the size of the atom is not easy to understand. But we have done it. And how we are going to measure it? Atomic radii are determined by measuring the distances between the centers of adjacent atoms with the help of X-rays or by spectroscopic measurements. How are we going to achieve it? We cannot find the exact radii of single atom, but we can find the exact distance or radius of any atom when it is bonded. So let us apply the concept on hydrogen molecule. You see in this picture two hydrogen atoms are bonded and we could measure the distance between their nuclei. Now when identical atoms are bonded, the distance between their nuclei is further divided to get radius of both hydrogen atoms, and that is 208 picometer. Now you must be surprised with this new unit of length. You know what is picometer? Picometer is the unit of length, which means 10 raised to the power minus 12 meter. You must be wondering why so low value? Because the atom size is very small and its radius is again a very smaller length. That's why smaller unit is used here. Now we see in this picture it is very obviously depicted that these balls are representing the size of the atom or the radii of atoms of all the periodic table elements. You see, in this periodic table, one can easily understand the size of the atom or the balls is decreasing as I move in a period, and the size gradually increases when I go down a group. Means whenever we compare the atomic radii of all the elements, there is a regular trend in their properties. So now another quest is that why it happens. If we talk in general, atomic radius increases down a group. Why? because there is a greater distance between the nucleus and the outermost orbital. This results in a larger atomic radius. Now I come back to the previous slide. The problem is the atomic radius is increasing down the group, but I have to discuss why it is happening. Because down the group, if we move in every period, there is a gradual increase in principal shell or the electronic shell. More shell, more number of electrons, and more space. And how it happens? If we take group number 1 elements. Group number 1 elements are also called as alkali metals. When I see the size of the lithium, lithium has 2 shells because it is in group 2, period number 2. But sodium has 3 electronic shells. And gradually, if I go down, there is an increase in electronic shell. So simply more shells, more space, more radius. But what happens in a period? Atomic radius decreases from left to right within a period. And why? This is just because of addition of one more proton and electron across a period. As I move in a period, one proton is added. In the same shell, one electron is added. So if we see, if one proton has a greater effect than one electron, thus electrons are pulled towards the nucleus. Now we see, with the help of example, this becomes very easy to understand. As I move in second period, the first element is lithium. And you know, when we study about the elements belonging to same period, the electrons are added in the same electronic shell. So in electronic configuration of lithium, we see the outermost shell has just one electron, but in beryllium, 2 electrons are added. These are not only 2 electrons, one more proton is added in the nucleus. In case of boron, one more proton results more attraction from the nucleus on these outermost electrons. And as I approach towards oxygen and fluorine, I see in the same shell 6 and 7 electrons are added. So fluorine experiences the minimum atomic radius in its period just due to the strongest nuclear force of attraction on the electrons, which results in the shrinking or the reduction of atomic size. I must be expecting the same trend of atomic radius in transition elements, but this is not very prominent, means the distance is not very larger. Why this is so? First, I see the distances in a period of transition elements. You know what transition elements are? Transition elements are the d block elements in which their outermost electrons come in d or subshells or d orbitals. So this is another case when the change is not very much greater. Again, when I see atomic distances or radii are almost similar, so the change is not very much prominent. Again a question comes, why this is not very much difference? Because of the intervening electrons. You know, d subshells have 10 electrons, a greater number of electrons to deal with, and due to these many number of electrons, they experience high shielding or screening effect. Now this screening effect is in fact the electron-electron repulsion, and due to this repulsion, the nuclear attraction becomes weaker on the outermost electron. That's why the atomic radii are not decreased to expected values. So this is the whole discussion which enable us to understand the behavior of atoms for their chemical bonding. Now, my next following classes will also be discussing few more properties such as electronegativity, ionization energies, and electron affinities. Now, by understanding these atomic properties and their behaviors and their trends in the periodic table, we will be very comfortable to understand the geometry of the compounds or the properties of compounds. Thank you very much. Wait for the next video. Till then, goodbye and take care.